Hello guys, welcome to Ncert Line by Line, and you are watching Ncert Revision series of Inorganic Chemistry. In this series, we will revise complete Ncert within a very small time, and I will tell you some tricks to remember and some very important concepts. So today in this video, we will see P block element of class 11th, and we will discuss about group 13 elements Boron family and group 14 elements Carbon family. And I will tell you how to remember inorganic chemistry in the end of the video. So now let's jump into the chapter. Variation in properties of the P block elements due to the influence of D and F electrons in the inner core of heavier elements makes their chemistry interesting. We will discuss in detail about it later, but remember that maximum deviations or exceptions that we are going to discuss in this chapter are due to the poor shielding effect of D and F electrons. Now about the general electronic configuration of P block elements. The general electronic configuration of P block element is NS2 and NP126, and the exception is helium, who does not have p electrons. It is called as P block elements because the last electron filled in p orbitals. There are 3 p orbitals and has maximum capacity of 6 electrons. So there are 6 groups present in P block from group 13 to group 18, having boron, carbon, nitrogen, oxygen, fluorine and helium head of the groups. Another most important property shown by P block elements is the variable oxidation state in a particular group. The maximum oxidation state shown by P block element is equal to the total number of valence electrons, that is the sum of s and p electrons. That is, if you take an example of aluminium having atomic number 13 and its electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p1, and we can also write it as like neon 3s2 and 3p1. In its outermost shell there are 3 electrons present, that is 2 in s orbital and 1 in p orbital. So its maximum oxidation state is +3. This is called as group oxidation state, which is shown by maximum number of the elements in a group. Clearly the number of possible oxidation state increases towards the right of the periodic table. But there is another oxidation state shown by heavier elements in the group due to inert pair effect, and whose value is generally less than 2 unit from the group oxidation state. Okay, so to explain this, let's see the table 11.1 from the book. As you can see in the table, in group 13, that is a boron family, the group oxidation state is +3 and the other oxidation state is +1, which is less than 2 unit from the group oxidation state. In carbon family, that is group 14, the general group oxidation state is +4, whereas the other oxidation states are +2 and -4. That means +2 is less than 2 from group oxidation state, plus -4 is not. So that's why it is written in book that P block elements may show other oxidation state who is normally but not necessarily differ from total number of valence electrons by unit of 2. That means it's generally less than 2 but not always. So you can see the other examples also, like nitrogen family, oxygen family. Now let's come to the next. In boron, carbon and nitrogen families, the group oxidation state is more stable for lighter elements in the group. However, the oxidation state 2 units less than the group oxidation state becomes progressively more stable for heavier elements in the group, and this happens because of the inert pair effect. Now, what is inert pair effect? Remember this line. Due to poor screening effect of D and F electrons, the electrons in s orbital become inert and do not participate in bonding. This is called inert pair effect, and due to this their oxidation state decreases by 2 units normally. Now let's come to the next paragraph. It says that non-metals and metalloids exist only in P block. Non-metallic character decreases down the group and metallic character increases down the group. This is obvious as you studied in periodic table. Okay, so let's come to the next paragraph. In general, non-metals have higher ionization enthalpy and higher electronegativities than the metal. Hence, in contrast to metals, which readily form cations, non-metals readily form anions. So ionization energy is the energy required to make an ion, or we can say the energy required to remove the outermost electron from its shell. So as we know, an important property of metal is to form cation. That means they lose electrons so easily. So they have very low ionization energy, and electronegativity is the property to attract lone pair of electrons. So as metal lose electron easily, so they have very low electronegativity also. That's the reason the compound formed by highly reactive metal with highly reactive metal are generally ionic, and between non-metals it is generally covalent. Another important point is non-metal oxides are acidic and metal oxides are basic, because non-metal oxides form acid when they react with water, that's why they are acidic, but metal oxides form base when they react with water, that's why they are basic. The first member of p block differ from the remaining members of their corresponding group in two major respects. First is the size and all other property which depends on size, and second is effect of d orbitals. Now this is interesting. This whole paragraph tells us that by using d orbitals, heavier elements can expand their covalency. See this line. Using these d orbitals, the third period elements can expand their covalence above 4. For example, while boron forms only Bf4 minus, aluminium gives AlF6 3 minus. So covalency is the number of covalent bond that an element can form. So here boron has maximum covalency of 4 and aluminium can expand its covalency by using d orbitals up to 6. And the other thing in this paragraph is the pi bond formation. Lighter elements form p pi multiple bond, whereas heavier elements form d pi and d pi multiple bond. Because lighter elements do not have d orbitals, so they can't form d pi multiple bond, so they only form p pi, and heavier elements form d pi and d pi multiple bond. And as d orbital has more energy, it's less stable than p orbitals, and this is general rule: more energy equal to less stability. The next and last thing in this paragraph is about the coordination number. Even an element is in same oxidation state, it can show different coordination number. As an example shown here about nitrogen and phosphorus, both have +5 oxidation state, but in NO3 minus it has coordination number of 3, whereas BO4 3 minus it has coordination number of 4. And it says that even two elements are in same oxidation state, they can show different coordination number. 13 elements, the boron family. So in the first paragraph, it is about metallic atoms. In general, when you go down the group, metallic atom increases. So boron is non-metal, aluminium is metal, but show some chemical similarity to boron. Gallium, indium, thallium are exclusively metal. So in next paragraph, it is a lot of data. The best way to remember is to revise again and again. So first thing is about boron. Boron is fairly rare elements, and there are some compounds, chemical composition that you should remember. First is orthoboric acid, that is H3BO3, borax Na2B4O7.10H2O, kernite Na2B4O7.4H2O, and in India borax occur in Puga Valley, Ladakh, Sambar Lake, Rajasthan. And the next thing is boron in earth crust is 0.0001% by mass, and it has two isotopes, that is boron 10 and boron 11. Boron 10 is 19% in earth crust and boron 11 is 81% in earth crust. Next about aluminium, it is the third most abundant in earth crust, that is 8.5% by mass, and the first is oxygen, that is 45.5%, and second is silicon, that is 27.7%. And there are some compound of aluminium that you should remember is bauxite, that is Al2O3.2H2O, and cryolite, that is Na3AlF6. Aluminium found in Mica, Madhya Pradesh, Karnataka, Odisha and Jammu. And the next thing is gallium, indium and thallium are less abundant in earth crust. Now next thing, 11.1.1 electronic configuration. We all know that the electronic configuration of p block is ns2 np1 to 6. So as this is group 13, the electronic configuration is ns2 np1. And the rest of the paragraph tells us that the gallium, indium has d electrons and thallium has d and f electrons. Now next thing, 11.1.2 atomic radii. In general, when you go down the group, atomic radius increases, and along the period atomic radius decreases, because in group new cells are added to the atom, but in period nuclear charges increases rapidly, resulting in a decrease in radius. But here is one exception present. The atomic radius of gallium is less than the atomic radius of aluminium because of poor shielding effect of d electrons. So you can see boron's atomic radius is less than aluminium, but aluminium's atomic radius is greater than gallium, and gallium's is less than indium, and indium's less than thallium. So remember this exception, this is very important. So next thing is 11.1.3 ionization enthalpy. In general, ionization enthalpy decreases down the group, but in boron family there is an exception. This is second exception and most important one. There is a trick to remember it. So see this table. Boron's fast ionization enthalpy is 801, whereas aluminum's fast ionization enthalpy is 577, which decreases rapidly. Then gallium's fast ionization enthalpy is 579, which again increases. Then indium's ionization enthalpy is 558, which then decreases. Then thallium's ionization enthalpy is 589, which again increases. So the best way to remember is decrease, increase, decrease and increase. Next thing is 11.1.4 electronegativity. Here is third exception in group 13. Electronegativity first decrease then increase rapidly. electronegativity of boron is 2, whereas aluminium is 1.5, which is decreased. Then gallium is 1.6, which increased. Then indium is 1.7, which again increased, and then thallium is 1.8, which again increased. So best to remember is first decrease in between boron and aluminium, then from aluminium to thallium it's increased. Now next is 11.1.5, the physical properties. Boron is a non-metallic, hard and black colored solid, high melting point, and rest of the members are soft and low melting point and high electrical conductivity. Electrical conductivity depends on the metallic character. More metallic character, more electrical conductivity, as they lose electrons easily. So as you go down the group, metallic character increases, so electrical conductivity also increases. Gallium exists as liquid in summer because of low melting point. Gallium has high boiling point, so it is used to measure high temperature. Density increases down the group. Remember this is very important, that density increases down the group. Next, 11.1.6, chemical properties. So first is oxidation state and trends in chemical reactivity. Due to small size of boron, the sum of its first 3 ionization enthalpies is very high. This prevents it to form +3 ions and forces it to form only covalent compounds. This means boron can't form ionic compounds, it only forms covalent compounds. As we go from boron to aluminium, the sum of the first 3 ionization enthalpy of aluminium considerably decreases and is therefore able to form Al3+ ion. And aluminium is also a highly electropositive metal. In the rest paragraph, it explains inert pair effect that I already explained before. So see this line, the relative stability of +1 oxidation state progressively increases for heavier elements, and the stability goes as aluminium's +1 state is less stable than gallium, gallium's less stable than indium, indium's less stable than thallium. Next, another important thing, in thallium, +1 oxidation state is predominant, whereas +3 oxidation state is highly oxidizing in nature. Now this line is very important as it connects this chapter with redox reaction, because it says that thallium generally show +1 oxidation state, but if it is present in +3 oxidation state, then it is oxidizing in character. That means it will act like an oxidizing agent. That means it will oxidize others and itself will undergo reduction. That means it will gain electron. So if we will see this in another way, if you will remove 3 electrons from thallium, it will obviously gain electron in a chemical reaction, so it will undergo reduction and will act like an oxidizing agent. These things are important. These basic things will improve your marks. Okay, so next is the compound in +1 oxidation state is more ionic than those in +3 oxidation state. Remember this line. This happens because of the large size, so more size, more ionic character. In next paragraph, in trivalent state, the number of electrons around the central atom in a molecule of the compound of these elements, example is boron in BF3, will be only 6. Okay, so see here, in boron, the outer electronic configuration is 2s2 2p1. So 3 electrons of boron and 3 electrons of fluorine will make 6 electrons around the central atom, that is boron, in BF3. So such electron deficient molecules have tendency to accept a pair of electrons to achieve stable electronic configuration and thus behave as Lewis acid. So in BF3, the central atom is surrounded by only 6 electrons, but for octet you need 8 electrons. So that's why BF3 is electron deficient and act as Lewis acid. Okay, so the tendency to behave as Lewis acid decreases with increase in size down the group. Next, BCl3 easily accepts a lone pair of electron from ammonia to form BCl3.NH3. So you can see the compound. So next is AlCl3 achieves stability by forming a dimer. Okay, so we'll discuss about this dimer later while studying diborane, because it will act like a banana bond or 3-center 2-electron bond or bridge bond. Okay, so in the next paragraph, remember 2 things. In trivalent state, most of the compounds being covalent are hydrolyzed in water, and trichlorides on hydrolysis in water form tetrahedral species, in which hybridization of M is sp3, as you see it clearly. The second thing is Aluminium chloride in acidified aqueous solution form octahedral species, and in which aluminium's hybridization is sp3d2. We'll discuss about this tetrahedral and octahedral species in few minutes later while we will study important trends and anomalous properties of boron. So the next thing is problem 11.1. This problem is very simple but very important problem. This problem teaches us a most important thing, that don't underestimate the power of the table of NCERT. Okay, so now let's see the problem. The standard electrode potential E minus for Al3 plus slash Al is minus 1.66 volt and that of Tl3 plus slash Tl is plus 1.26 volt. Predict about the formation of M3 plus ion in solution and compare the electropositive character of the two metals. Okay, so let's go to the table 11.2 and find the answer. Okay, so in the table we almost discuss everything: atomic number, atomic mass, electronic configuration, atomic radius, in which a exception present between aluminium and gallium, ionic radius, ionization enthalpy, and as you can clearly see, the 3 ionization enthalpy of boron is too much higher than aluminium. That's why boron can form ionic compounds, it only form covalent compound. Okay, so we all discussed about it before. Electronegativity, the first, it decreases from boron to aluminium, then it increases from aluminium to thallium. Next is melting point. This is important. Here is a star question present. See this melting point in between boron and aluminium decreases, in between aluminium and gallium it again decreases, but in between gallium and indium it increases, and between indium and thallium it again increases. So remember this: decrease, decrease, increase and increase. This will help you to remember melting point. And the data, you should not remember the numbers, just remember this: it first decrease, then again decrease, then increase and increase. Okay, now for our question, electrode potential value. Remember, more negative electrode potential value, more stable ion. The more negative electrode potential value, the more easily form ion. As you can see, for M3 plus slash M, aluminium has minus 1.66 and thallium is plus 1.26. So for Al3 plus slash Al is more stable than thallium 3 plus slash thallium, and opposite for M plus slash M value. So our question was predict the formation of M3 plus ion. So M3 plus ion for aluminium will be more stable than thallium, and electropositive character for aluminium 3 plus ion is more than. But if question was asked about the electropositive character of aluminium plus ion and thallium plus 1 ion, then thallium plus 1 is more electropositive than aluminium plus 1. But as it asks about aluminium 3 plus ion, it is more stable than or more electropositive than thallium 3 plus ion. Now next is reactivity towards air. First, boron is unreactive in crystalline form. Aluminium form thin oxide layer for protection, but amorphous boron and aluminium react with air to form B2O3, that means boron trioxide, and Al2O3, that means an aluminium trioxide, and they form nitride at high temperature with dinitrogen. So here you can see the equations. So here E means the elements of group 13. So when group 13 element react with oxygen, it will form 2E2O3, and when they react with nitrogen, it will form 2En or metal nitride. So in next paragraph, it is important. Nature of oxide vary down the group. Acidic character decreases and basic character increases. So B2O3 or boron trioxide is more acidic and react with basic metallic oxide to form metal borates. Aluminium and gallium oxides are amphoteric and indium and thallium are basic. Remember this nature of oxide: acidic character decreases and basic character increases. The next is reactivity towards acid and alkali. Boron does not react with any acid or alkali, but aluminium reacts with both acid and alkali. Thus, it is amphoteric in nature. Aluminium dissolves in dilute HCl and aqueous alkali and liberate hydrogen, but nitric acid makes a protective layer on the surface of aluminium and makes it passive. Next is reactivity towards halogen. Okay, so these compounds react with halogen to form trihalide, but the exception is TLI3, thallium trihalide. Okay, this is important. Remember this. This happened because both have large size. So thallium and iodine has both large size, that's why they can form TLI3. So see this reaction: 2E plus 3X2 gives rise to 2EX3, and here X means fluorine, chlorine, bromine and iodine. Next is problem 11.2. White fumes appear around the bottle of anhydrous aluminum chloride. Give reason. So the answer is anhydrous aluminum chloride is partially hydrolyzed with atmospheric moisture or atmospheric water to liberate HCl gas. Moist HCl appears white in color. So next is 11.2. Important trends and anomalous properties of boron. See this line: the trichloride, bromide and iodide of all these elements, being covalent in nature, are hydrolyzed in water. Species like tetrahedral and octahedral except boron exist in aqueous medium. That means in water ionic compounds break down easily or hydrolyzed easily. Example is NaCl in aqueous medium. It forms Na plus and Cl minus, but trichlorides, bromides and iodides of group 13 elements, being being covalent, hydrolyzed in water and form tetrahedral and octahedral species. But the exception is boron because its maximum covalency is 4. Next, the monomeric trihalides being electron deficient are strong Lewis acids. Monomeric trihalides are electron deficient and are strong Lewis acid. As we saw this type of examples before, like BCl3 react with NH3 and form BCl3.NH3 where a coordination bond present. So here an example of BF3 present, that is BF3 plus NH3 gives rise to BF3 coordination bond NH3. So all this happen because boron does not have d orbital, so it can expand its covalency beyond 4. Here in this paragraph one important thing is present. See this line, most of the other metal halides like ACl3 are dimerized through halogen bridging. Example is Al2Cl6. So this is 3-center 2 electron bond or banana bond or bridge bond or halogen bridging. We will discuss about it a few minutes later while we will discuss diboron. Next is problem 11.3. Boron is unable to form BF6-3-. Explain. So the answer is simple. Boron can't expand its covalency above 4 because it does not have d orbitals. Next, 11.3. Some important compounds of boron. Here we will read about borax, orthoboric acid and diboron. So first is borax. It is a white crystalline solid. Formula is Na2B4O7.10H2O. It has tetrahedral unit is B4O5OH 4 and 2 See this image. So tetranuclear unit means it consists of 4 atoms and which repeat itself to give a structure. So here 4 boron repeat itself to give a ring-like structure. The correct formula of borax is Na2B4O5OH 4.8H2O. Borax dissolve in water and form NaOH and orthoboric acid and its alkaline. Next part about the formation of borax bead. See this line. On heating, borax first loses water molecule and swells off. On further heating, it turns into a transparent liquid which solidifies into glass-like material known as borax bead. See this reaction. On heating borax, it gives sodium metaborate, that is Na2B4O7, and on further heating, it gives 2NaBO2 and boric anhydride, that is B2O3. Anhydride means remove of hydrogen by using water. So here we can say B2O3 is an anhydride of boric acid. It has the same formula as boron trioxide but different formation process. So now this paragraph is important. Metaborates of many transition metals have characteristic color and used in laboratory as borax bead test to identify them. For example, when borax is heated in Bunsen burner with CaO, that means cobalt oxide, on a loop of platinum wire, a blue colored cobalt borate or CoBO2 2 bead is formed. Next is 11.3.2 orthoboric acid. So formula is H3BO3. It is a crystalline solid with soapy touch. It is sparingly soluble in water but highly soluble in hot water. Then its preparation. It can be prepared by two methods. So first one is acidifying an aqueous solution of borax, that is Na2B4O7 plus 2HCl plus 2H2O gives rise to 2NaCl plus 4BOH 3. This is the method that is written here, but the second method we studied in borax, if you remember, that Na2B4O7 plus 7H2O gives rise to 2NaOH plus 4H3BO3, that is orthoboric acid. So if you don't pay attention, you are going to miss these kind of things. So next is, it is also formed by hydrolysis, reaction with water or dilute acid of most boron compounds like halides and hydrides. So that means BX3 plus H2O gives rise to BOH 3. Okay. Next is, it has a layer structure in which planar BO3 joined by hydrogen bond. You can see this in figure. Okay, so next paragraph. This paragraph has some good concepts. So boric acid is a weak monobasic acid. It is not a protonic acid but acts as a Lewis acid by accepting electrons from hydroxyl ion. So when you see closely first line and second line contradicting each other, that means in first line it said that it is a weak monobasic acid. That means it gives only one H+. But in second line it said that it is not a protonic acid. That means it do not give H+. Okay, so solve this doubt. Let's see the problem 11.4. Why boric acid considered as a weak acid? Because it is not able to release H+ ion on its own. It receives OH- from water molecule to complete its octet and in turn release H+ ion. So it's not a protonic acid because it does not give H+ on its own in aqueous condition like HCl, H2SO4 and HNO3 gives gives H plus. So that's why it's not a protonic acid but a weak monobasic acid. Next, on heating, orthoboric acid above 370 Kelvin forms metaboric acid HbO2, which on further heating yields boric oxide, that means B2O3. So you can say that B2O3 is an anhydride of H3BO3. This is the main reason why this paragraph is there. In exam it can ask what is the anhydride of orthoboric acid. Remember, anhydride is formed when we remove all hydrogen by using water. So 2H3BO3 minus 3H2O gives rise to B2O3. We already discussed the problem 11.4. So next, 11.3.3 diboron or B2H6. Here a lot of data you have to remember. So remember it point by point. So this is the simplest boron hydride known. Then its preparation. There are three ways to prepare it. First is, it is prepared by treating boron trifluoride with lithium aluminium hydride in diethyl ether. So 4BF3 plus 3 lithium aluminium hydride in the presence of diethyl ether gives rise to 2B2S6 plus 3 LiF plus 3 AlF3. So the second method is the laboratory method, which is the oxidation of sodium borohydride with iodine. So 2NaBH4 plus I2 gives rise to B2S6 plus 2NaI plus S2. So the third preparation is the industrial method of preparation. By the reaction of BF3 with sodium hydride, it is prepared. So 2BF3 plus 6NaH gives rise to B2F6 plus 6NaF. So B2F3 plus 6NaH in 450 Kelvin gives B2S6 plus 6NaF. Next, diboron is a colorless, highly toxic gas with a boiling point of 180 Kelvin. It catches fire spontaneously upon the exposure to air. It burns in oxygen, releases an enormous amount of energy. As you can see in this reaction, when it reacts with oxygen, it produces boron trioxide, and you can see the enormous amount of energy, that is minus 1976 kilojoule per mole. Next is, most of the higher borons are also spontaneously flammable in air, and the reaction will be same as the above. So next, borons are readily hydrolyzed by water to give boric acid. See, till now we saw total 3 preparation of boric acid, that is H3BO3 or BOH3 in different places. One we saw in borax, second we saw in orthoboric acid, and third here, that is B2S6 plus 6H2O gives rise to 2BOH3 plus 6H2. Next, diboron undergo cleavage reactions with Lewis base, that is represented as L, to give boron adduct, that is BH3.L, and there is a coordination bond present in between them. So here you can see the reactions. B2S6 plus 2NMe3 gives rise to 2BH3.NMe3. So you can see the coordination bond present. So you can see another example, that is B2S6 plus 2CO gives rise to 2BH3.CO. So next, this paragraph is very important. Direct question comes from this paragraph. So ammonia with diboron gives initially B2S6.2NH3, which is formulated as BH2NH3 whole 2, then whole plus BH4 whole minus. Further heating gives borazine, that is B3N3S6, known as inorganic benzene, in view of its ring structure, which alternate BH and NH groups. Remember this chemical reaction completely, an inorganic benzene or borazine formula, that is B3N3H6. So you can see the reactions. 3BH2 plus 6NH3 gives rise to 3BH3NH3 whole 2, then whole plus, and BH4 whole minus, which on heating gives 3B3N3H6 plus 12H2. So remember this complete reaction. Next paragraph is about banana bond in B2S6. I told you 2 pages before that we will discuss banana bond in diboron while we saw AlCl3 structure. Here you can see that again. See in this structure, there is a diamond shape present in the center formed by 2 aluminium and 2 chlorine, in which the bond length between aluminium and chlorine is 221 picometer. But in normal case, outside of the diamond shape, the bond length between aluminium and chlorine is 206 picometer. So that's what we can see from this structure. So now let's come back to diboron. So see this, the 4 terminal hydrogen atom and the 2 boron atoms lie in one plane. Above and below this plane there are 2 breathing hydrogen atom present. So see this diagram, 4 hydrogen and 2 boron are in one plane, and 2 banana bonds in above and below that plane. Next, the 4 terminal BH bonds are regular 2-centered 2-electron bonds, while the 2 bridge bonds, that is BHB bonds, are different and can be described in terms of 3-centered 2-electron bond or banana bond. So see this, there are 4 normal boron hydrogen bonds present where one bond is formed by 2 electrons usually, but there are 2 3-centered 2-electron bond or 2 banana bond present where 3 centered are formed by 2 boron and 1 hydrogen, but 2 electrons present in between them. And remember that the banana bond length is usually more than the normal bond length, as we saw in AlCl3, and you can see here in B2S6 also. The normal BH bond length is 119 picometer, but banana bond length it's 134 picometer. Next, boron also forms a series of hydroborates. Hydroborates means anions that only contain hydrogen and boron. The most important one is tetrahedral, that is BH4 whole minus ion. Tetrahydroborates of several metals are known. Lithium and sodium tetrahydroborates are also known as borohydrides. This is very important, and it is prepared by the reaction of metal hydrides with B2S6 in diethyl ether. You can see the reaction. 2MH plus B2S6 gives rise to 2M plus BH4 whole minus, and here M is lithium or sodium. Next is lithium borohydride, that is LiBH4, or sodium borohydride, that is NaBH4, are used as reducing agents in organic synthesis, and they are useful starting materials for preparation of other metal borohydrides. Mark this line, this is very important. In exams, direct question asked from this, that which one is used as starting material for preparation of other metal borohydrides. So mark this line. Next, 11.4 uses of boron and aluminium and their compound. Here no such thing to explain, so I will just read it. Boron is extremely hard, refractorily solid, of high melting point, low density, low electrical conductivity. It has many applications, like boron fibers are used in bulletproof vest and light composite material for aircraft. Boron 10 has high ability to absorb neutrons, and therefore metal borides are used in nuclear industry as protective seals and control rods. The main industrial application of borax and boric acid is in the manufacture of heat resistant glasses, that is pyrex, glass wool and fiberglass. Borax is also used as a flux of soldering metals for heat, scratch and strain resistant glazed coating of earthenwares and as constituent of medicinal soaps. An aqueous solution of orthoboric acid is generally used as a mild antiseptic. Aluminium is a bright silvery white metal with high tensile strength. It has a high electrical and thermal conductivity. On weight to weight basis, the electrical conductivity of aluminium is twice that of copper. That means if you take two same weight of aluminium and copper, aluminium will show twice electrical conductivity than copper. Aluminium is used extensively in industry and everyday life. It forms alloy with copper, manganese, magnesium, silicon and zinc. Aluminium and this alloy can be given shapes of pipe, tubes, rods, wires, plates or foils, and therefore find uses in packing, utensil making, construction, aeroplane and transportation industry. The use of aluminium and its compounds for domestic purposes is now reduced considerably because of their toxic nature. 11.5 Group 14 elements, the carbon family. Members of this group are carbon, silicon, germanium, tin and lead. Carbon is the 17th most abundant element by mass in earth crust, and as we saw in boron family, that most abundant element in earth crust is oxygen, that is 45.5%. Second is silicon, that is 27.7%. Third is aluminium, that is 8.3% by mass. And here carbon is 17th most abundant element, so remember that. Next, it is present in nature in free as well as in combined state. In free or elemental state, it is available as coal, graphite and diamond. However, in combined state, it is present as metal carbonate, hydrocarbons and carbon dioxide gas, that is 0.03% in air, as you all know that. Next, carbon is the most versatile element in the world because it is present in almost everything from living tissue to drug and plastics, and it is an essential constituent of all living organisms. Next, it has two stable isotopes, that is carbon 12 and carbon 13, and the third isotope is radioactive, that is carbon 14, and its half-life is 5770 years, and it is used for radiocarbon dating. and this technique radiocarbon dating is used to know the age of the dead organisms. Next, silicon is the second most abundant on Earth crust, that is 27.7% by mass, and present in nature in the form of silica and silicates, and silicon is the most important component of ceramics, glass and cement. Germanium occur in traces, tin occur as cassiterite, SnO2, and lead as galena and PbS. Next, ultra pure form of germanium and silicon are used to make transistors and semiconductor devices. Okay, so that was all about the introduction or the basic thing you should know about the carbon family. So make a note of this and revise as much as you can. Okay, so now let's see some important topics. Next is 11.5.1 electronic configuration. So the general electronic configuration of carbon family is Ns2 Np2. So now let's see the next 11.5.2 covalent radius. So covalent radius increases from carbon to lead, as you can see in the table also, but from carbon to silicon the increase in covalent radius is high, but from silicon to lead very small increase in radius observed. This is due to the presence of completely filled d and f orbitals in heavier elements. As I told you in the beginning of this chapter, that most of the exceptions that you are going to see in this p block element is due to the d and f electrons. So you can see that here also. So now let's see the next 11.5.3 ionization enthalpy. So the first ionization enthalpy of group 14 members is higher than the corresponding members of group 13. That's interesting. Now the influence of inner core electron visible here also. That's obviously the effect of inner core electrons is visible in almost every atom. Next, in general, ionization enthalpy decreases down the group, but here from carbon to tin, ionization enthalpy decreases, but between tin and lead it increases slightly. But the reason, can you guess? Yeah, again the d and f electrons, poor shielding effect. So you can remember it like in carbon family, ionization energy first decreases from carbon to silicon, then again decreases in silicon and germanium, then again decreases in germanium and tin, but in the last it increases in between tin and lead, but the increase is very slight. Next, 11.5.4 electronegativity. Group 14 elements are slightly more electronegative than group 13 elements, and it's due to the small size, because as we go from left to right in the periodic table, the atomic radius decreases, so electronegativity increases. Here another interesting thing that you can see, electronegativity of carbon is 2.5, silicons is 1.8, germaniums 1.8, tins 1.8, and leads 1.9. So as you can see, from silicon to lead the electronegativity is almost same. So now it's easier to remember, as silicon, germanium, tin and lead has almost same electronegativity. Next, 11.5.5 physical properties. Okay, so all members of group 14 are solid, carbon and silicon are non-metal, germanium is a metalloid, and tin and lead are soft metals. Soft metal means these are easy to work or cut easily without breaking. Next, melting point and boiling point of group 14 elements are much higher than those of corresponding group 13 elements. So remember that. Next is 11.5.6 chemical properties. So first point is oxidation state and trends in chemical reactivity. Okay, so let's see this. In this complete paragraph, most of the things have similar concept as boron family. So I think you will find it easier to understand. Okay, so group 14 elements have 4 electrons in outermost shell, and we saw that in electronic configuration Ns2 Np2 there are 2 electrons in S subshell and 2 electrons in P subshell. So that means net 4 electrons in its outermost shell. Common oxidation state are +4 and +2, and carbon also show negative oxidation state. Example is CH4, in which the carbon's oxidation state is -4. Next, the sum of the first 4 ionization enthalpy is very high. Compound in +4 oxidation state are generally covalent in nature, and heavier members show +2 oxidation state because of inert pair effect, that is inability to use NH2 electrons of valence shell due to poor shielding effect of D and F electrons. So as we go down the group, +2 oxidation state become more stable. So germanium's +2 oxidation state is stable than tin's +2 oxidation state, which is less stable than lead's +2 oxidation state, and the relative stability of these two oxidation states vary down the group. That is, as we go down the group, +4 oxidation state become less stable and +2 oxidation state become more stable. As you can see in this line also, carbon and silicon mostly show +4 oxidation state. Germanium forms stable compound in +4 state and only few compound in +2 state. Now pay attention very closely. Next two lines are very important. These two lines connect this chapter to redox reaction. I already explained once before this type of concept in boron family. So let's see here also. Tin forms compound in both oxidation state. Tin in +2 oxidation state is a reducing agent. So tin in +2 state is a reducing agent. That means it will reduce others in a chemical reaction and itself undergo oxidation. That means it will lose electron, because oxidation means lose electron. Remember this. So Sn+2 lose electron to form Sn+4. And you can add another line here in NCERT that Sn+4 is more stable than Sn+2. So that's why Sn+2 act as a reducing agent and itself will undergo oxidation. Next, lead in +4 oxidation state is an oxidizing agent. As it's written here, lead in +2 is more stable. So from lead +4, so it will try to go lead +2, and for that it will gain electron, and gain of electron is a reduction. So as it will itself undergo reduction, it will act like a oxidizing agent. So that's why lead in +4 oxidation state act as a strong oxidizing agent. Next, in tetravalent state, the number of electrons around the central atom in a molecule, that is carbon in CCl4, is 8. So these are electron precise molecule. That means they neither donate nor accept electron. So they neither Lewis acid nor Lewis base. So next is carbon's maximum covalency is 4. It can expand its covalency beyond that because it has no d orbital, but the other members can expand their covalency. That's why species like SiF6 2-, GeCl6 whole 2-, SnOH6 whole 2- exist where hybridization of central atom is sp3d2. Next, reactivity towards oxygen. All members when heated in oxygen form oxides, and there are two types of oxides, that is monoxide and dioxide, that is MO and MO2 respectively. And SiO, that means silicon monoxide, exist only in high temperature. Next, oxides in higher oxidation states of elements are generally more acidic than those in lower oxidation state. So if you take an example of silicon dioxide, that means SiO2, and silicon monoxide, that means SiO, SiO2 is more acidic because it is in +4 oxidation state, and silicon monoxide is less acidic because it is in +2 oxidation state. The dioxide, carbon dioxide, silicon dioxide and germanium dioxide are acidic, whereas SnO2 and PbO2 are amphoteric in nature. Carbon monoxide is neutral, germanium oxide is acidic, whereas SnO and PbO are amphoteric in nature. These things are very important. Direct questions come from this in NEET, JEE or any exam in which chemistry is there. So remember this. Next, problem 11.5. Select the members of group 14 that forms most acidic dioxide, and that is commonly found in +2 oxidation state. And third question is used as semiconductor. So the answer of first question is most acidic dioxide formed by carbon, lead found in +2 oxidation state commonly, and silicon and germanium are used as semiconductor. Okay, so next, reactivity towards water. Carbon, silicon and germanium are not affected by water. Tin decomposes steam to form dioxide and dihydrogen gas. That is, Sn plus 2H2O gives rise to SnO2 plus 2H2. Lead is unaffected by water, probably because of protective oxide film formation. Next, reactivity towards halogen. Carbon family form MX2, that is dihalide, MX4, that is tetrahalide. Except carbon, all other members react directly with halogen under suitable condition to make halide. Most of the tetrahalides, that is MX4, are covalent where central atom is sp3 hybridized with tetrahedral shape, but the exception is SnF4, that is tin tetrafluoride, and PbF4, that is lead tetrafluoride. Those are ionic in nature. Next, PbI4, that is lead tetraiodide, do not exist because this lead and iodine bond can't excite CS2 electron from the ground state. Next, heavier elements make dihalides because they have more stable +2 oxidation state, and as obvious, stability of dihalide increases down the group and stability of tetrahalide decreases down the group. And it's also shown here that is germanium tetrahalide is more stable than germanium dihalide, whereas lead dihalide is more stable than lead tetrahalide. Next, Except CCl4, that is carbon tetrachloride, other tetrachlorides are easily hydrolyzed by water because the central atom can accommodate the lone pair of electrons from oxygen atom to water molecule in d orbitals. You can see here also in SiCl4, that is silicon tetrafluoride, undergo hydrolysis to form salicylic acid, in which all chlorine atoms are replaced by hydroxyl group, that is bond OH. Next, problem 11.6. SiF6 whole 2 minus is known, whereas SiCl6 whole 2 minus not. Give possible reasons. So the answer is, the main reasons are 6 large chloride ions cannot accommodate around Si4 plus due to limitation of its size. Second is, interaction between lone pair of chloride ion and Si4 plus is not very strong. So this is the reason why SiF6 exists whereas SiCl6 does not exist. Next, 11.6, important trends and anomalous behavior of carbon. Carbon has a small size, higher electronegativity, higher ionization enthalpy, and no d orbitals. So it's different from others and so anomalous behavior. And it can't expand its covalency beyond 4, and it only form p-pi multiple bond with itself and with other atoms of small size and higher electronegativity like oxygen, sulfur, nitrogen. But heavier elements do not form p-pi bonds because their atomic orbitals are too large and diffuse to have a effective overlapping. Next, carbon atom have a tendency to link with other through covalent bond to form chains or rings. This property is called catenation, and down the group catenation power decreases because size increases and electronegativity decreases. So you can see carbon's catenation power is very high than silicon's, and silicon's is higher than germanium, but germanium and tin has nearly equal catenation power and lead does not show catenation. In the table you can see that carbon-carbon single bond enthalpy is more and tin's bond enthalpy is very less, and lead do not form bond with itself. That means it does not show catenation. Next, due to property of catenation and p-pi bond formation, carbon is able to show allotropic form. Okay, so now let's see some allotropes of carbon. So next is 11.7, allotropes of carbon. So here we are going to see 3 allotropes of carbon, that is diamond, graphite and fullerene. Diamond and graphite are crystalline form of carbon and fullerene is the amorphous form of carbon. Fullerene is discovered in 1985 by H.W. Kroto, E. Smalley and R.F. Curl, and they won Nobel Prize in 1996 for this. Now let's see 11.7, diamond. It has a 3-dimensional crystal lattice. Each carbon is sp3 hybridized. That means each carbon is linked to 4 other carbon atoms in a tetrahedral fashion, and carbon-carbon single bond length is 154 picometer. The structure extended in space and produces a rigid 3D network of carbon atom in which only covalent bond is present. Due to this extended covalent bond, it's so difficult to break, and diamond is the hardest substance on earth, and it is used for sharpening of hard tool, in making dyes and in manufacture of tungsten filament for electric bulb. Next, problem 11.7, diamond is covalent yet it has a high melting point. Why? So the answer is, diamond has a 3-dimensional network involving the strong carbon-carbon single bond which are very difficult to break and in turn has a high melting point. So next is 11.7.2, graphite. Okay, so it has a layer structure. In one layer, each carbon atom is sp2 hybridized and form a planar hexagonal ring. So one carbon is directly bonded to 3 other carbon atoms by sigma bond, and the carbon-carbon sigma bond length is 141.5 picometer, and the last electron forms a pi bond which is delocalized in the whole sheet. That's why graphite conducts electricity. 2 layers in graphite are held by a van der Waals force, and the difference between 2 layers is 340 picometer. Graphite breaks easily in between the layers, so that's why it's soft and slippery and used as a dry lubricant in machine running in high temperature where oil can't be used as lubricant. Okay, so next is 11.7.3, fullerene. Fullerenes are made by heating up graphite in an electric arc in the presence of inert gases such as helium and argon. The sooty material formed by the condensation of vaporized CN small molecules consists of mainly C60 with smaller quantity of C70 consisting of even number of carbon atoms up to 350 or above. Fullerenes are the only pure form of carbon because they have smooth structure without having dangling bonds. Dangling means hang freely. That means means in fullerene there is no hanging bond or dangle bond. Fullerenes are cage-like molecules. C60 has a soccer ball shape and called Buckminster fullerene. So if you remember that in the next chapter, that is organic basic concept, there is a paragraph about fullerene in which it says that Buckminster fullerene is a common name for C60 and we generally don't use its IUPAC name because it is more complicated and lengthy. So next, it contains 26 membered rings and 12 5-membered rings. A 6th-member ring is fused with only 6 or 5-membered ring, but a 5-membered ring can only fuse with 6-membered ring. Each carbon atom is sp2 hybridized. That means there is only 3 sigma bond and 1 delocalized pi bond present, which give aromatic character to the molecule. It has 60 vertices occupied by each carbon atom. Single bond length is 143.5 picometer. Double bond length is 138.3 picometer. Again, in organic basic concept, we will see about hybridization, and we know that S character is inversely proportional to bond length. That means more S character, less bond length. That's why sp2 carbon has less bond length than sp3 hybridized carbon. Next, spherical fullerenes are also called buckyballs in short. So as you can see in the diagram, it looks like a soccer ball or football. So next, graphite is thermodynamically most stable allotrope of carbon and therefore del F of graphite is taken as 0. So remember this carefully. If a question asked what is thermodynamically most stable allotrope of carbon, then its answer is graphite, not diamond, not fullerene. Reason is graphite has a great van der Waals force of attraction in between its layers and also a delocalized pi electron, which makes graphite's melting point more than diamond. So it's thermodynamically more stable than diamond. This is another reason why graphite is used as a dry lubricant in machines running in high temperature. Next, del F value of diamond and fullerene, that means C60, are 1.90 and 38.1 kilojoule per mole respectively. That means diamond is thermodynamically more stable than fullerene. You can see the values. More positive value, more thermodynamically unstable. Next, other forms of elemental carbon like carbon black, coke and charcoal are all impure forms of graphite or fullerene. Carbon black is obtained by burning hydrocarbon in a limited supply of air. Charcoal and coke are obtained by heating wood or charcoal respectively at high temperature in the absence of air. So remember this. Next, 11.7.4 uses of carbon. So first is graphite. Graphite fibers embedded in a plastic material form high strength light-weighted composites. The composites are used in products such as tennis racket, fishing rod, aircraft and canoes. Canoes means a narrow light-weighted boat for 2 people. Next, being good conductor, graphite is used for electrode in batteries and industrial electrolysis. Crucibles made from graphite are inert to dilute acids and alkali. Crucible means a pot in which metals are melted. Second, charcoal. Being highly porous, activated charcoal is used in absorbing poisonous gases. Also used in water filters to remove organic contaminators and in air conditioning system to control odor. Next, carbon black. Carbon black is used as a black pigment in black ink and as a filler in automobile tires. Next is coke. Coke is used as a fuel and largely as a reducing agent in metallurgy. So I will again explain. Reducing agent means it will reduce others and itself undergo oxidation. And oxidation means loss of electron, so it will lose electron. Okay. Next is diamond. Diamond is a precious stone used in jewelry. We all know that. And measured in carat. 1 carat equal to 200 milligram. Next, 11.8. Some important compounds of carbon and silicon. There are 2 oxides of carbon, that is carbon monoxide and carbon dioxide. The first is 11.8.1 carbon monoxide. Okay, so direct oxidation of carbon in limited supply of oxygen or air produce carbon monoxide. 2C plus O2 gives rise to 2CO. For a small scale preparation, pure carbon monoxide is prepared by dehydration of formic acid with concentrated H2SO4 at 373 Kelvin. HCOH gives rise to H2O plus CO in the presence of concentrated H2SO4 at 373 Kelvin. On commercial scale, it is prepared by the passage of steam over hot coke. The mixture of carbon monoxide and hydrogen thus produced is known as water gas or synthesis gas. Carbon solid plus H2O gas gives rise to carbon monoxide plus water and together it is called as water gas, and the temperature is in between 473 to 1273 Kelvin. Next, when air is used instead of steam, a mixture of carbon monoxide and nitrogen is produced, which is called producer gas. You can see that here also. 2 carbon plus oxygen plus 4 nitrogen gives rise to 2 carbon monoxide plus 4 nitrogen, which is together called as producer gas, and the temperature is 1273 Kelvin. There is only one thing to notice. For production of producer gas, more temperature is required than for the production of water gas. You can see in the reactions also. Next, water gas and producer gas are very important industrial fuel. Carbon monoxide in water gas and producer gas can undergo further combustion, forming carbon dioxide with liberation of heat. Okay, so next is carbon monoxide is a colorless, odorless and almost water insoluble gas. It is a powerful reducing agent and reduces almost all metal oxides other than those of alkali and alkaline earth metal, aluminium and a few transition metals. This property of carbon monoxide is used in the extraction of many metals from their oxide ores. This is a very important property of carbon monoxide. There is another concept about oxidation and reduction, that adding of oxygen is oxidation and removal of oxygen is reduction. This is actually an old concept. This only applicable to the compounds have oxygen. Don't worry about this. All these concepts are explained in the redox reaction chapter. So if you see here, Fe2O3 plus 3CO gives rise to 2Fe plus 3CO2. So here oxygen is removed from Fe2O3 and make iron. So Fe undergo reduction and CO undergo oxidation and act like a reducing agent. Second example is ZnO plus CO gives rise to Zn plus CO2. Okay, next, carbon monoxide has 1 sigma bond and 2 pi bond, and carbon has a lone pair of electrons. So it is an electron rich compound and act like an electron donor. So they react with certain metals, and in the presence of heat they produce metal carbonyls. Metal carbonyls are coordination compounds between transition metals and carbon monoxide. Next, carbon monoxide is poisonous because it makes complex with hemoglobin, which is 300 times more stable than oxygen hemoglobin complex. So this prevents oxygen molecule to reach cells and ultimately death. The next is 11.8.2 carbon monoxide. First is its preparation. It is prepared by complete combustion of carbon and carbon containing fuel in excess of air, that is carbon plus oxygen gives rise to carbon dioxide. Methane or CH4 plus 2 oxygen gives rise to CO2 plus 2 H2O. Next, in laboratory, it is prepared by the action of dilute HCl on calcium carbonate. CaCO3 plus 2 HCl gives rise to CaCl2 plus CO2 plus H2O. On commercial scale, it is obtained by heating limestone. It is a colorless and odorless gas. Its low solubility in water makes it immense biochemical and geochemical importance. With water, it forms carbonic acid H2CO3, which is a weak dibasic acid. Dibasic acid means it gives 2H plus in aqueous solution. In Boron family, we saw orthoboric acid, which was a weak monobasic acid, that is, it gives only 1 H plus. Next is carbonic acid dissociate in 2 steps. H2CO3 plus H2O gives rise to HCO3 minus bicarbonate ion plus H3O plus. Then bicarbonate ion plus H2O gives rise to CO3 2 minus or carbonate ion plus H3O plus. H2CO3 or HCO3 minus buffer system helps to maintain pH of blood between 7.26 to 7.42. Being acidic in nature, it combines with alkali to form metal carbonates, that example like calcium carbonate CaCO3. Carbon dioxide, which is normally present in the extent of 0.03% by volume in the atmosphere, is removed from it by a process known as photosynthesis. It is a process by which green plants convert atmospheric carbon dioxide into carbohydrates such as glucose. So you can see the reactions here. 6CO2 plus 12H2O gives rise to C6H12O6 plus 6O2 plus 6H2O in the presence of chlorophyll and H-mu. H-mu is the light energy. By this process, plants make food for themselves as well as for the animals and humans. Unlike carbon monoxide, it is not poisonous, but increase in combustion of fossil fuel and decomposition of limestone for cement manufacture in recent years seems to increase the carbon dioxide content of atmosphere. This may lead to increase in greenhouse effect and thus raise temperature of the atmosphere, which might have serious consequences. Next, carbon dioxide can be obtained as a solid in the form of dry ice by allowing the liquefaction liquefied carbon dioxide to expand rapidly. Dry ice is used as a refrigerant for ice cream and frozen food. Gaseous carbon dioxide is extensively used to carbonate soft drinks. Being heavy and non-supporter of combustion, it is used as a fire extinguisher. A substantial amount of carbon dioxide is used to manufacture urea. Next, in carbon dioxide, carbon atom is sp hybridized. Two sp hybridized orbitals of carbon atom overlap with two p orbital of oxygen atom to make two sigma bond, while two other electron of carbon atom are involved in p-pi bonding with oxygen atom. So the shape of carbon dioxide is linear and the bond length is 115 picometer with no dipole moment, and resonance structure of carbon dioxide is shown here. Next, 11.8.3 silicon dioxide SiO2. 95% of Earth's crust is made up of silica and silicates. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. Quartz, cristobalite, and tridimite are some of the crystalline forms of silica, and they are interconvertible at suitable temperature. Now about silicon dioxide. Silicon dioxide is covalent three-dimensional network solid in which each silicon atom is covalently bonded in tetrahedral manner to 4 oxygen atoms. Each oxygen atom in turn covalently bonded to another silicon atoms as shown in diagram 11.6. Each corner is shared with another tetrahedron. The entire crystal may be considered as a giant molecule in which 8-membered rings are formed with alternate silicon and oxygen atom, as you can see in this diagram here. Next, silica in its normal form is almost non-reactive because of very high silicon-oxygen bond enthalpy. It resists the attack by halogens, dihydrogen, and most of the acids and metal, even at elevated temperature. However, it is attacked by HF, hydrogen fluoride, and NaOH, sodium hydroxide. So you can see these reactions here. SiO2 plus 2NaOH gives rise to Na2SiO3 plus H2O, and second one is SiO2 plus 4HF, SiF4 plus 2H2O. Next, quark is extensively used as piezoelectric material. It has made possible to develop extremely accurate clocks, modern radio and television broadcasting, and mobile radio communications. Piezoelectric material mean the material that stores charge. Silica gel is used as a drying agent and as a support for chromatography material and catalyst. Kieselguhr, an amorphous form of silica, is used in filtration plants. Next, 11.8.4 silicons. They are group of organosilicon polymers. They have R2SiO as a repeating unit. The starting material for the manufacture of silicons are alkyl or aryl substituted silicon chlorides, that is RnSiCl4-N, where R is the alkyl or aryl group and N is the number of alkyl and aryl group. When methyl chloride react with silicon in the presence of copper as a catalyst at temperature 573 Kelvin, various type of methyl substituted chlorosilane of formula MeSiCl3, Me2SiCl2, Me3SiCl with small amount of Me4Si are formed. Here Me means methyl, Si means silicon, and Cl means chlorine. Hydrolysis of dimethyl dichlorosilane, that is CH3 SiCl2 followed by condensation polymerization yield straight chain polymer. Okay, so you can see this here, 2CH3Cl plus silicon in the presence of copper powder at 570 Kelvin form dimethyl dichlorosilane, that is CH3 SiCl2, which undergo hydration, that means addition of water, releases two HCl molecule and form CH3 SiOH2, that means dimethyl dihydroxysilane, and dimethyl dihydroxysilane undergo polymerization and release water molecules to form silicons. The chain length of polymer can be controlled by adding dimethyl dichlorosilane, that is CH3 SiCl, which is added at the end of the polymer. As you can see here, when you add another dimethyl dichlorosilane, a water molecule again releases and it polymerizes and increases the length of silicons. Next, silicons being surrounded by non-polar alkyl groups are water repelling in nature. They have in general high thermal stability, high dielectric strength, and resistance to oxidation and chemicals. They have wide applications. They are used as sealant, grease and electrical insulator, and for waterproofing of fabrics. Being biocompatible, they are also used in surgical and cosmetic plants. So these were some uses and some property of silicons. Next, problem 11.8. What are silicons? Simple silicons consist of SiO, or we can say R2SiO as a repeating unit, in which alkyl or phenyl groups occupy the remaining bonding position on each silicon in the above structure that is present. They are hydrophobic or water repellent in nature because they are surrounded by non-polar alkyl groups. Next, 11.8.5 Silicates. A large number of silicates mineral exist in nature. Some of the examples are feldspar, zeolites, mica, and asbestos. The basic structural unit of silicates is SiO4 4-, in which silicon atom is bonded to 4 oxygen atom in tetrahedron fashion. In silicates, either the discrete unit is present or a number of such units are joined together via corners by sharing 1, 2, 3 or 4 oxygen atom per silicate units. So this means either a single structural unit SiO4 4- is present, or 2 or 3 basic structural silicate units joined together to form a large structure, and the joining is oxygen atom of one unit is joined with the silicon atom with another unit. When silicate units are linked together, they form chain, rings, sheet or three-dimensional structures. Next, negative charge on silicate structure is neutralized by positively charged metal ions. If all the 4 corners are shared with other tetrahedral unit, three-dimensional network is formed. So that means the negative charge is balanced by a metal ion, so they react with metal to form metal silicates, and if they join together they form a 3D network. We saw that before. So two important man-made silicates are glass and cement. So you can see this diagram 11.7. Here it shows the tetrahedral geometry of silicates, and in second structure it shows the representation of SiO4 4- unit, where a dot represents silicon and O represents oxygen. So you can clearly see the tetrahedral structure from the above view. Next, 11.8.6 Zeolites. If aluminium atoms replace few silicon atoms in three-dimensional network of silicon dioxide, overall structure known as aluminosilicate acquires a negative charge. Cations such as Na+, K+, and Ca2+ balance the negative charge. Examples are feldspar and zeolites. Zeolites are widely used as a catalyst in petrochemical industry for cracking of hydrocarbons and isomerization. Example is ZSM5, a type of zeolite used to convert alcohols directly into gasoline. So remember this example and its function. It converts alcohol directly into gasoline. Next, high-heated zeolites are used as ion exchangers in softening of hard water. So remember its second function also, that it is used to softening of hard water. So that was all about P block of class 11th. So if you want to remember complete NCERT, then revise each chapter minimum 5 times. First 3 times by watching video and 2 times by hearing audio. I will upload audio format of this complete video in Spotify and all other platform also. So while hearing audio, if you can imagine that page from NCERT and the picture of that page comes in your mind, the diagrams, the paragraph and the heading, then you have mastered that chapter. Do it with one chapter, then you will see the result. So that was all I wanted to tell you, and all the other chapters playlist link is in the description, so it won't be difficult to find any video. So if you have any doubt or suggestion, comment below. I will must reply that because I don't have that much subscriber right now. Okay, so bye, see you in the next video.